Yes, as Dirk indicated, I'm going to talk to you guys today about some of the work that I do in brain behavior relations and aphasia. And specifically, this project is a collaboration between the the clinical aphasia research group that I belong to at the VA Pittsburgh healthcare system, and some folks in the Department of Neurosurgery at the University of Pittsburgh, and lately at Stanford University. Dr. Juan Fernandez Miranda, a neurosurgeon who's my primary collaborator on the project, was at Pitt when we got the work funded a few years ago, and earlier this year he took a position at Stanford. Our mutual collaborator, Frank Ye, remains at Pitt, and he's also an essential part of the project, along with everyone else that's contributed to it. So I'm going to first just lay out the three primary aims of this project that sort of correspond to the sets of results that I'm going to talk about today. The first of these is we set out to sort of have a look at determining what the particular white matter pathways are that support word production in aphasia. Second, we wanted to determine whether the integrity of particular white matter tracts could predict who might benefit from aphasia rehabilitation. And last, we wanted to have a look at whether the behavioral improvements we see with aphasia rehabilitation are associated with increases in structural brain connectivity. So to provide some background for that first aim, I'll talk about something that I suspect a lot of the audience here is familiar with, Greg Hickok and David Pupple's influential dual-stream model of language. And the basic notion here is that there are two distinct networks that sort of connect the posterior language areas in the posterior temporal lobe and parietal lobe with the anterior language areas, and that's by a dorsal stream shown here in blue that functions primarily to map sound to motor patterns and articulation, and then a ventral stream shown in red here that serves to map sound to meaning and meaning to sound. The next slide shows an alternative presentation of the same model from Dorothy Sauer and her group in Germany, and it's a little bit more specified with respect to the white matter substrates. And this was an investigation where they used essentially functional localizer tasks, sentence repetition for the dorsal stream and auditory comprehension for the ventral stream, and used fMRI data from those tasks to define seed regions for DTI-based tractography to have a look at what the white matter substrates of the two streams were. And unsurprisingly, they identified the arcuate fasciculus as a major component, white matter component of the dorsal processing stream. And on the ventral side, they identified the extreme capsule and the middle longitudinal fasciculus. So while it's pretty well established that the arcuate is the major white matter component of the dorsal stream, there are a number of other candidate tracks that have been proposed as anatomical white matter substrates for the ventral pathway, the ventral processing stream. And in addition to the middle longitudinal fasciculus and the extreme capsule, there have been some of the others discussed include the inferior fronto-occipital fasciculus shown here in sort of teal that connects the occipital lobe to the inferior frontal lobe, and the inferior longitudinal fasciculus shown in orange, and also the hook-shaped fiber bundle, the uncinate fasciculus that connects the anterior temporal lobe to the inferior frontal lobe. And in fact, together the IFOF, the inferior fronto-occipital, and the uncinate fasciculus actually form part of the extreme capsule, and are not always differentiated from it. So another sort of current in literature that sort of informed this investigation is some work that's been done on the internal structure of the arcuate itself. So while it's well established, it's anatomically dorsal, and it's clearly contributes to dorsal streams, the dorsal stream in a functional sense. This sort of influential paper from 2008 identified a sort of internal structure to the arcuate, again based on fMRI data collected from healthy individuals. And these investigators identified two distinct pathways. A pathway shown here in green that primarily connects the superior temporal gyrus to the inferior frontal lobe, and a middle temporal gyrus pathway shown in orange, with the former, the green pathway, being specialized for phonology and repetition, and the orange one being specialized for lexical-semantics. And in fact, they proposed that that this component of the arcuate part of its function is to assign meaning to spontaneous speech. And the next slide here just shows a schematic of the representation of the same thing. This work was followed up on by my collaborator, Juan, who used diffusion spectrum imaging-based high-definition fiber tractography to sort of have a closer look at the cortical terminations of the arcuate. And he found evidence for the same kind of internal structure that Glasser and Rilling wrote about, with the sort of inner superior temporal gyrus pathway and the outer middle temporal gyrus pathway. And this follows some it's organized in ways that one would expect, with the sort of inner pathway being more strongly left lateralized in terms of volume and number of connections. And so this, so there's some question as to whether the extent to which, although the arcuate fasciculus is dorsally located, it might also participate functionally in the ventral processing stream. There are some authors, including R.D. Roloffs, with the Weaver ++ arc model of naming, has sort of expressed agreement with this, but then there are folks on the other side as well who take the position that the semantic processing and even assignment of meaning to spontaneous speech occurs through the ventral processing stream. There we go. And so then there's one sort of final piece of background to this work that I want to talk about, and this is another piece that I expect lots of folks in the audience are familiar with, and this is Gary Dell's interactive two-step model of word production, the SP variant. And so this is it's a two-step computational model of word production or picture naming, where deciding to say a word or seeing a picture activates a network of conceptual semantic features. And that activation spreads through a network of bidirectional connections to a second lexical-semantic layer that's it's encoded for meaning and syntax, but not for sound. And then having selected the lemma or lexical-semantic representation, the activation spreads further to phonological representations that are selected and assembled for output to the motor system. And one of the sort of primary virtues of this model for our purposes in this particular investigation is that it's useful for modeling the data of individual subjects with aphasia. So given given data from a naming test, one can use some tools that have been developed to develop estimates of S or semantic weight parameters and P or phonological weight parameters that sort of govern how effective a given individual is at accomplishing each of these two steps, and use these essentially as ability estimates in each of these two domains. And there's been some work done over the past few years sort of relating these model parameters, or both the model parameters themselves as well as the data that go into them to the brain. And so these are data from one voxel lesion symptom mapping study demonstrating that lesions to dorsal stream areas tend to be more associated with phonological paraphasias, non-word outcomes when on a picture naming task, and lesions to ventral stream areas, shown here in purple, are more associated with semantic paraphasias. That is, errored words that are related to the target by meaning. And in a later study, Gary Dell and colleagues actually related the S and P parameters from his interactive two-step model to lesions in much the same way in a voxel lesion parameter mapping study. And they found that the P weight parameter was negatively associated with damage to dorsal stream areas, essentially. And while the lesion sites that were associated with S weight were perhaps predictably more diffuse and spread out, when they controlled for total lesion volume, the voxels that you see that sort of overlap with the dorsal stream areas sort of dropped out of the analysis, and essentially it was areas in the anterior temporal lobe and inferior frontal lobe that's sort of consistent with notions of dual stream cortical nodes that were associated with the S weight parameter. And so, sort of against this background, our first sort of cross-sectional question in this study is, what are the white matter associations with S and P? And that's sort of the first question that we set out to answer. And so I'm going to present data from 42 participants with aphasia due to left hemisphere stroke. With these characteristics, about a quarter of them had some co-occurring apraxia of speech. They were all, as I said, in the chronic phase, and had lesions confined to the left hemisphere. So on the behavioral side, we administered the Philadelphia naming test and got error counts for the sort of Dell model scoring convention. So each response was counted as correct. A semantic error, a formally related error, mixed, that is both semantic and formal, an unrelated real word error or non-word error, and we fit those error counts to the Dell model using Grant Walker's online fitting algorithm, and got these connection weight estimates S and P for each participant. On the imaging side, each participant received a diffusion weighted scan, a diffusion spectrum imaging scan, and the major feature of this approach, the way that it's distinguished from DTI, from diffusion tensor imaging, is that it's capable of resolving multiple fiber orientations within each voxel. So the reconstruction algorithm, whereas the reconstruction algorithm enables reconstruction of an orientation distribution function, which is essentially a probability distribution rendered on the surface of a sphere. And so you can take sort of the maxima of that probability distribution function as sort of the fiber orientations. And that's sort of in contrast to DTI, which models water diffusion in the brain as an ellipsoid that can resolve only a single fiber orientation within a voxel. And so this enables the method to do a better job of representing fiber crossings and in any place where you have sort of sharp angles in fiber deflection. So this approach, this diffusion spectrum imaging approach, can be used to drive ROI-based tractography, but the particular analysis approach that we've settled on for this study is a different one developed by our collaborator Frank Ye, and that is local connectometry. And this slide sort of differentiates this local connectometry approach from global connectometry approaches that are more that have been more commonly used to date, at least. And so whereas global connectometry relies on cortical parcellation and end-to-end tracking of connections between cortical parcels, local connectometry defines the local connectome as the degree of connectivity between adjacent voxels. And local fiber orientations from a common atlas are used together with spin distribution functions from the diffusion weighted data to essentially define this local connectome for individual subjects. And this slide shows a schematic of the processing pipeline. So the diffusion weighted data are reconstructed in a standard space, and the local fiber orientations from a common atlas are used to sample the spin distribution functions, and then from that's developed this connectivity matrix that can be represented as a matrix across individuals. And having done that, we can then correlate it with behavioral variables of interest, in this case the S and P weight parameters that I talked about before. And then having identified sort of the subcomponents of the fascicles that are correlated with the behavior, we can track those along a common pathway to identify the components of fascicles that are associated with the behavior of interest. And having done that step, permutation statistics on the length histograms of the identified components can be used to develop false discovery rates so that we can have some sense of the confidence in our findings. All of this occurs in the DSI Studio application that was developed by Frank Ye. And here on the slide, I'm just showing some of the sort of input parameters. So we identified a length threshold of 20 millimeters for any of the tracks that we identified in the analyses I'm going to present. Required a T statistic of at least 2 for identifying associations. And in all the analyses I'm going to talk about, we controlled for total lesion volume. So this slide shows the results for the correlations with S weight. So these are all of the fascicles, subcomponents of fascicles that were positively correlated with the S weight parameter. That is mapping of conceptual semantic to lexical semantic representations within the Dell model. And we see a lot of what we expected to see here. We see ventral-stream pathways, including the middle longitudinal fasciculus in light blue, the uncinate in orange, and the IFOF in magenta. Interestingly, we also find that the posterior arcuate, shown here in purple, is also represented as being positive, its connectivity being positively correlated with S weight. And that, sort of is, I think, that's interesting, given that most presentations of the dual stream model focus on the arcuate's functional contribution to the dorsal stream. This would suggest that although it's clearly dorsally located, it also, at least in this sample of partially recovered folks with chronic aphasia, participates in the assignment of meaning to words and what would be considered a ventral stream function.
Oh, sorry. So, you compute a measure of connectivity within a tract, right? Like within a given fiber, right?
Yes.
So how do you compute that? Or is it just sorry.
So it's based on it's this measure developed from the spin distribution functions from the diffusion weighted data, and essentially so my understanding is clearly at the conceptual level. Frank handles the math, but as I understand it, so we're modeling the diffusion of water as a way to represent the connectivity of voxels within the brain, and so the more directional the diffusion, the more white matter structure we infer. Mm-hmm. And so to the degree that water diffusion within adjacent voxels is directional and oriented in the same direction, one can infer a higher degree of connectivity between those two adjacent voxels. That's my understanding of how the method works. Mm-hmm. Unfortunately, I'm not able to talk in more technical detail about the math behind it, but that's...
And this probably won't work with DTI, right?
Correct. It requires DSI data. That's right. Yep. So so in addition to these core language pathways that we sort of expected to see, we find connectivity of the posterior corpus callosum and the cingulum, and also the fornix. Shown here in this sort of darker blue color, sort of running beneath the splenium of the corpus callosum on the right, are also showed positive associations with the S weight parameter. And I'll have more to say about that in a couple minutes. This slide shows the positive correlations with P weight, and here again the results are sort of broadly consistent with what we expected. In addition to finding cingulum and posterior corpus callosum, we find the posterior arcuate is well represented, along with sort of subsegments of the middle longitudinal fasciculus on the left. And again, as would be predicted from the data that have gone into the dual stream model and building it, the correlations with P weight are more strongly left lateralized than they were for S weight, where we had bilateral representation of the IFOF in that analysis. This slide shows superimposed upon one another the posterior arcuate streamlines that were positively correlated with both S and P. And the point of this slide is to simply show that they're pretty interleaved with one another, and there's no real support here for a strong functional subdivision within this posterior arcuate segment based on these data at least. And in fact, in my conversations with Juan and Sandeep, the postdoc that's handled most of the segmentation, their read of this is that sort of anatomically all of these streamlines are sort of in what would be considered the middle temporal gyrus pathway, that outer pathway that was talked about in the Glasser and Rilling paper and in Juan's earlier study of the arcuate. And that may have something to do with the fact that a large proportion of our sample may simply not have much connectivity in that inner superior temporal gyrus pathway of the arcuate due to their lesions. So these results are, to my eyes, broadly consistent with dual stream neurocognitive models of language. We have S being associated with anatomically ventral pathways bilaterally, and we find associations with P that are more dorsal and more strongly left lateralized. The one sort of nuance here is that it does appear, at least in this sample, that the arcuate fasciculus participates in some fashion in lexical-semantic as well as phonological aspects of word production. So one of the things that we didn't really expect going in was to find associations with connectivity and limbic pathways. And I'm going to focus this discussion here on the fornix for a moment. It's the major output pathway of the hippocampus, and via the corpus callosum, it connects the hippocampus to the pre and post central gyri, as well as the parietal lobe. And so this is kind of interesting to think about, because we typically think of semantic memory, or I was trained to think of semantic memory as distinct from episodic memory, but it does appear that episodic memory plays a role, or may play a role, in language learning, language recovery from aphasia, and possibly, and there's also some evidence that the hippocampus may play a role in online language processing as well. So this notion that language is not just, it's not all just abstraction of the signal that comes in through our ears, right? We actually use episodic information, whether that's the identity of a speaker and peculiarities about their voice to drive lexical phonological processing, or specific episodic traces related to that might relate to meaning to enable us to build semantic representations. These are all ways in which the hippocampus and hippocampal circuits might participate in language. And then there's the more recent work coming out of Melissa Duff's lab, who presented in this forum last week, suggesting that in addition to those components, that the hippocampus may also have a role in online language processing for the purpose of not only retrieval and binding of information across modalities, but perhaps also prediction, as well as processing pronoun reference and other things. So moving on now to sort of the longitudinal aims that I had articulated. I'll go into now talking about our efforts to look at whether connectivity of particular white matter pathways could predict who would benefit from aphasia treatment, and also having a look at whether behavioral improvements in aphasia treatment are reflected in upregulation of connectivity. And so there are a few findings in literature that have already demonstrated both of these findings in other contexts. So out of this group here and at MUSC in Charleston, there's this finding that global connectivity measures of the left temporal lobe were predictive of improvement on a measure of overall aphasia severity in the context of naming rehabilitation. And likewise, Emily McKinnon recently published this study showing that treatment-related reductions in the number of semantic paraphasias were associated with increased integrity of the left inferior longitudinal fasciculus. This study, this might get to your question a little bit. So she used diffusion kurtosis imaging, which I understand is sort of can be done with DTI data, or can be done with it doesn't require a DSI sequence to generate the data. Yeah. And to my read, it gets pretty much, and Leo, Dr. Bonilla had given me this impression, it gets at pretty much the same thing that the DSI-based HDFT analyses get at. It sort of it can resolve multiple fiber orientations within a box.
I know it goes in that direction, right? So it's the set of analysis is kind of like it has more kind of like protrusions, but not the distributions that you showed on the side.
And then last, I'll just point out this finding from Van Hayes showing that naming treatment was actually, in their study, it was a combination of semantic feature analysis and phonological components analysis, was associated with significant increases in generalized fractional anisotropy of the left arcuate. And so, I don't think, I'm not sure that any of those findings were actually out at the time that we proposed this study, but essentially what we did is we sort of combined forces with a VA trial of semantic feature analysis that recently finished up that was headed up by Mike Dickey and Pat Doyle. And so as part of that protocol, so 18 of the individuals from the 42 that I presented the cross-sectional data on also went through that protocol. And as part of that protocol, they received about 60 hours of semantic feature analysis treatment for naming over the course of 4 weeks. And of those 18, 3 received a DSI scan at treatment exit as well. So they all received scans the week they started treatment and then immediately after finishing treatment. And for measuring outcomes, we tested these patients on sets of trained and untrained items prior to treatment. We probed them weekly during treatment and at treatment exit and at 1 month follow-up. And they also got, as a measure of overall aphasia severity, the comprehensive aphasia test, from which we calculated the modality mean t-score, which is correlates really highly with the law of AQ. It's a measure of overall aphasia severity that we prefer. And I'll show you behavioral data for all 3 time points, out to the 1 month follow-up. The connectometry that I'm going to present is all looking at prediction of outcomes at treatment exit or correlations with change at treatment exit. So these data are actually an update of data that Mike Dickey presented here, I think it was about a year ago from this trial. And so this is actually from the larger subsample that, the larger group, not just the 16 or 18 individuals, but the trends are the same. And in this work, we find, in addition to finding a robust effect on trained items, a much weaker effect on untrained, the trained items being here in green, a much weaker effect on untrained items in red, we find interesting interactions with S weight and P weight, such that folks with higher S weight tend to respond better to the treatment, both for trained and untrained items. And that's shown here, just sort of schematically. Here are the interactions with P weight, where we find that folks with higher P weight get a better treatment response for trained items, but not for untrained items, which is, as Mike presented last year, sort of what you would expect. If the semantic system is more robust, it's sort of that's the part of the system that's better able to generalize the practice and learning or establishment of connections that might go on in a treatment like semantic feature analysis, where the focus is really on establishing semantic associations with the target word to be named, as opposed to practicing its phonological form. Although there is practice of the phonological form, because on every trial you say it once, if not multiple times. And the next few slides just show posterior histograms of predictions from the model, and are simply sort of function as credible or confidence intervals about the data that I showed you before. So essentially what I'm showing here on this slide is that for treated items, both S weight and P weight were sort of significantly predictive of better outcomes. And this slide makes the point that for S weight here, we're getting, for folks with higher S weight, in this case operationalized as I think 1 standard deviation above the mean versus 1 standard deviation below the mean on S weight, are getting more effect on untreated items, whereas for folks with high P weight, that interaction is not present. And then this last slide simply shows sort of the 4-way interaction between S weight and P weight and item type, that is, whether it was a trained item or an untrained item, and we see that there's this robust interaction favoring S weight, essentially showing that S weight positively affects treatment response for both trained and untrained items, whereas P weight positively impacts treatment effects only for trained items. And then the last behavioral slide I'll show, these are the results of essentially Bayesian t-test on the change in CAT modality mean t-score, so overall aphasia severity for just the subsample of 16 individuals that were scanned at pre and post. And so we have essentially a 99% probability that the mean is greater than 0. And the slide on the right just shows the actual, in red, it shows the histogram of the actual CAT modality mean change scores, along with posterior predictive replications of the data. So we get, it's not overwhelming change, so we're getting a little bit less than 1 t-score point on the CAT, but it is quite statistically reliable, even in this relatively small sample. So to get at the question of what pathways, what fiber pathways are predictive of treatment response, we correlated the connectivity matrix collected from the pre-treatment DSI scan with change scores on overall aphasia severity, and as well as the probe measures, the trained and untrained probes. And so this slide shows the tracts that were predictive of change in aphasia severity. And these results mirror in large part the results we found for the S-weight parameter in the larger cross-sectional sample. Again, we have the uncinate, the IFOF, and the middle longitudinal fasciculus, three sort of major components of the ventral processing stream represented, as well as the posterior arcuate, and along with portions of the IFOF on the right, and temporal and parietal connections of posterior corpus callosum, and along with components of the internal capsule, mostly the posterior limb, and some of those at least are connections to the thalamus. For untreated naming probes, we find a different set of results, so much more focused on the ventral stream with the uncinate and the IFOF and the anterior corpus callosum represented, along with the right fornix again, here in blue. When we ran the analysis on the treated probes, the results looked essentially the same as these results for overall aphasia severity, but the false discovery rate was something like 40%. So that's, I don't have a slide for it. There were no reliable associations with the treated probes. I would suspect in a sample this small that might be related, and you know, given the fact that we're talking about 15 items, that sampling error is one likely explanation for that difference. So, and then for the final aim, we correlated, so we took the difference between the pre and post-treatment connectome matrices. So the connectome matrix developed at time 1 and time 2, you simply take the difference of them, and then you can correlate. You can either look for change in that. You can look, essentially do a one sample test to see if there's change in that connectome matrix, and you can also, using multiple regression, correlate it with behavior. So when we did the test of whether the connectome matrix had changed on average, the finding was completely null. There was no average upregulation of connectivity in any particular place in the brain. However, when we correlated that difference matrix with behavior, we found some interesting results that are shown here for the aphasia severity variable. Again, so we have here, and in these, what we see is that the pathways in the right hemisphere are a little bit more strongly represented, but again, we're finding ventral stream pathways, mainly the IFOF, again, more prominently represented on the right than on the left. We're finding a few streamlines in the right arcuate fasciculus. We're finding the right uncinate fasciculus. We're finding, again, posterior corpus callosum and cingulum. And then the other thing that's new here is the cerebellar peduncles are showing up. And that's sort of consistent across all of these correlations of behavior with change. You'll see that on the next slide here as well. And these are, so this is correlating the pre-post difference matrix in connectivity with the treated naming probes. And here we see the arcuate is well, the arcuate and the IFOF are both well represented on the right. On the left, we have some portions of the posterior IFOF and a little bit of the left middle longitudinal fasciculus. Again, the uncinate on the right, and all three cerebellar peduncles are represented as well. And so in this particular analysis, the false discovery rate for the untreated probes was again unacceptably high. It was up around 15%, not as high as the previous one for the treated probes, but again high enough that it's probably not worth interpreting to any great degree. And it actually showed less than this one for the treated naming probes. It was mainly focused on the the right IFOF and the cerebellar pathways that are shown here. And so what these analyses suggest to us is that response to behavioral treatment is associated with increased connectivity. So response both in terms of predicting response as well as looking at upregulation of connectivity associated with treatment. That's associated with the core language pathways in both hemispheres. And that also we have, again, limbic and cerebellar pathways playing a role. And so I've already spoken a little bit about, the potential role for the limbic pathways, at least the connections between the hippocampus and the language processing system via the fornix. So, I'll speculate here a little bit about the cerebellum. There is this literature that's been around for a while, suggesting that right and left cerebellar lesions can lead to impairment of semantic functions in language. In addition, there's a nice review of fMRI research on the cerebellum, suggesting that both semantic and phonological tasks activate contralateral cerebellum. That is, so in folks with typical language dominance on the left, the right cerebellum will be activated in antonym generation kinds of tasks, phonemic fluency tasks, and that sort of thing. And then lastly, the last thing I'm going to refer to here is Rajani Sebastian's work on TDCS to the right cerebellum, where she has found that can improve generalization of aphasia treatment, both in the context of I believe, writing treatment as well as naming treatment. So, and that's been the sort of the, I mean, perhaps it should not have been the surprising part of this to me, but we went in with a set of predictions about ventral versus dorsal stream and sort of this semantic contribution of the arcuate. And indeed, initially we set out with a sort of ROI-based tractography analysis strategy, and then sort of moved to this connectometry approach part of the way in. And so, and I think that it's a real virtue here because of the sort of bottom-up data-driven approach where we're not as constrained by our initial hypotheses and can find things that link up with other parts of the literature productively. So, all right, well, that went a little bit faster than expected. I'll close out by acknowledging our funding sources, NIDCD, as well as the Veterans Affairs Rehabilitation Research and Development Service have supported this work along with some local pilot project funding along the way. And obviously a large team of individuals, research clinicians, doc students, and postdocs, both in our group at VA Pittsburgh that's shown here in the picture, as well as folks that were in Mon's lab at Pitt, and people that are in his lab now at Stanford. So that's what I have. I'm happy to take your questions.
We'll do questions from the room first, and if people online have questions, they can type them in the chat box, and I will read them out as well.
So in your sample, did you have like how bad was the initial impairment?
Yeah, so I can go back to the descriptive slide. It was on average moderate. We had a few people that were quite severely impaired, but if memory serves, just get back to the slide. So yeah, so our average aphasia severity T-score was 53, so that's about a third of a standard deviation above the mean, and it's fair. There was a standard deviation of 6, right? So you expect 10 in the population, so it's a little bit tight. But we had a few people that were quite severely impaired, a lot that were moderately impaired, a few that were mildly impaired. So it was reasonable distribution.
How sensitive do you think the P and the S variables are to more nuanced differences between aphasia types and subtypes and types of semantic disorder and apraxia of speech versus real phonological retrieval problems? I always have the feeling that particularly P is highly contaminated by apraxia of speech, and it makes perfect sense that there is not just one type of semantic disorder, but there can be different categories, right? So how does that come into Bayesian symptom mapping in this sense?
Yeah.
Does that account for the widespread of the areas that you found? Yeah.
Perhaps, yeah. So there's sort of two parts of the question, the one about P and then the one about S, right? So, regarding the contamination by apraxia speech, that is absolutely the case, right? And so, yeah, sort of on a methodological note, there's this lenient scoring rule that's been applied historically at times to the Philadelphia naming test, where if you have a person with aphasia who has a concomitant apraxia speech, when you're scoring their PNT, you kind of give them one phoneme for free. At least that was how it was articulated initially. We have not adopted that rule at VA Pittsburgh because I think it's an attempt to sort of deal with that issue, but I think it muddies more than it clarifies. And so, so to answer your question directly, like P weight is highly contaminated by apraxia speech, and so that, yeah, there's no, in fact, Grant Walker's sort of extension of Gary's model, is an attempt, I think, at, well, it's more an attempt at explaining conduction aphasia than it is dealing with apraxia speech in any serious way. But it gets at his and obviously Greg Hickok's work on sort of articulating how the phonological system talks to the motor system and trying to explicate that. But there's no at the level that we're operating at, there's no good way of doing that at present. I also just phenomenologically have found P weight to be less stable. Like and by that I mean smaller changes, and then so it's non-word errors mainly that drive P weight. So if you make lots of non-word paraphasias, your P weight's going to go down. And I think to a lesser extent that's true of formals, but I think formal, like the real word errors, tend to impact S weight more. And what I find in if you when we're doing our reliability work, if you if there's just a small change in the number of non-word errors, you can get what appear to be relatively large changes in P weight.
That might also account a little bit for the correlation you found between P and S weights, right? Given that you had this track where both of them seem to weigh on the same area.
Although S and P weight do not themselves correlate, and Gary's model is set up that way. I think that's by design, and I found it to be very reliable finding. In any behavioral set I've ever looked at, the correlation between them is essentially null, and that's the case here too. So that sort of, if anything, makes that finding that the streamlines in the arcuate that are correlating positively with them, are so intermingled when those two variables don't actually correlate with one another. Now I haven't run it in this sample of, that was the large sample of 42, and I'm confident that correlation is, it's 0.1 at best. I haven't looked at it in a while. Yeah. Mm-hmm.
How do you distinguish between the pathways that are damaged and the gray matter that's damaged? These tend to be obviously simultaneously damaged. So this criticism applies equally to cortical damage reports. But I guess that's my question: is how much of it is actually pathways versus the centers themselves that are damaged?
Right. Well, to my understanding, this analysis shows correlations with the with structure, or with connectivity defined in the way that I talked about it. Now, could you pick up additional variants if you also were to include in the model, cortical damage? I would think, yeah. And I think Julius is doing work on that right now, right? Or has published some work on that, combining, cortical and tractography-based or DTI-based measures of connectivity, and that's something I've thought about, but don't have any good answers as to how to include both of those in a predictive model. You could imagine doing it in a regression model, but it seems like there ought to be something a little bit more sophisticated. And my sense is, at least I thought I had seen an abstract or something that Julius was headed in that direction, if he didn't already have it solved.
So in addition to correlating your connectivity with the S&P, did you try to correlate it with the scores, with the from P.T. or anything like that?
Yeah, so we did correlate it with the overall aphasia severity metric.
Yeah.
And it shows pretty much what you'd kind of expect. It showed a lot of the same stuff we get from S weight. And in fact, S correlates pretty highly with overall aphasia severity, as opposed to P, where the correlation is much weaker. But S predicts aphasia severity reasonably well. I think the correlation is like 0.8, and so predictably you get results that look a lot like the results we got for S weight. A little more robust because it's a more reliable measure, I think, because so much information goes into it. Yeah, and I have not gone into correlating the individual. I've done a little bit of it, but not. I don't place too much stock in going and correlating the individuals, like subtests from the cat, like looking at repetition versus comprehension because those are also highly correlated. That I think my expectation would be that you'd find essentially the same results for all of them because they correlate so highly in aphasia. And I think to have a go at that, you'd want to look at some residualized scores where you're factoring out that sort of general dimension of aphasia severity and looking at repetition or name your function residualized on aphasia severity. And
so what would be your clinical takeaway from this information?
Yeah, so that's a good question. I think clinically, as one of the postdocs in our lab put it to me recently after going to the session on aphasia treatment in the brain at ASHA, one clinical message is that as a clinician, you don't need to know about the brain quite yet, but it's coming, right? I mean, that's one promise of this. It's a little flip, but right. I mean, the goal here is to get to a point where we can look at a collection, ideally, of behavioral measures and maybe neuroimaging measures, maybe things based on this sorts of white matter imaging, and predict what kind of treatment will work best for a given individual, and know what to prescribe for them based on that. And I think it's obviously still a ways off. So that's one thing. So stay tuned because that may be coming. The other thing is it does, the other message that I would give to clinicians from this is that it does seem that treatment is changing structure in the brain, right? I mean, we're getting correlations with behavior. We're getting increased white matter structure that are correlated with behavioral changes that we believe are the direct result of this treatment. And that seems like a powerful message, not only for clinicians but also for patients. You can change your brain. Now, what are those changes? That's a whole nother can of worms. But those are the two things that I would probably take from it right off the top of my head, anyway.
Yeah, so let's change those changes along the tracks that were correlated, or along the streamlines, I should say, that were correlated with improvement, right? Did you see anything weird? Did you see anything that how to say that, like, did all the correlations go in one direction? Or
Yeah, good question. So there are some negative correlations that I'm not showing you because I don't know how to think or talk about them yet.
Specifically called you out.
And in fact, so we're working on the manuscript for the first cross-sectional analysis right now, and I think the negative correlations will make it into that. Mm-hmm. But yeah, there are. So one of the things that's a little surprising, you'll notice that the go to slide. There we go. So yeah, let's go to the lesion overlay. I thought I was go to. So here's the lesion overlay for this sample, right? And so that red hotspot sits right on the inferior arcuate fasciculus. Mm-hmm. And so from that perspective, maybe it's not so surprising that all of our positive correlations were with the posterior arcuate. And in fact, in some of the analyses, we find negative correlations between behavior and the anterior arcuate. And so, and then it gets hard to think about and talk about really quickly, but so we have less connectivity predicting better behavior. How do you think about that? One way it might make sense is that, given that this is a sample of people with aphasia due to left hemisphere stroke, is that the people with better connectivity in the inferior arcuate are probably people with lesions in the posterior cortex. Yeah. And maybe just maybe that like those posterior lesions are what really drives down the behavior or drives down the potential for improvement. And
You
it's
have
just
to have a lesion.
if you have exactly.
Yeah.
If you've got to have a lesion somewhere, maybe it's better to have it anteriorly. That might be, but I'm, I didn't put that in pictures because I'm not sure. But that's what I think yet.
So it seems to me that that's the perfectly reasonable way to think about these negative correlations. Like, so not only does behavior correlate with lesions, but lesions also correlate with other lesions negatively or positively. If you have one in A, you're not going to have one in B.
Yeah.
And in some cases, if you have one in A, it's really likely that you're also having one in C. So related to that, do you think that some of that might account for your fornix turning up, for example? Just because it's really close to another pathway that is actually the real culprit here. But if you have a lesion there, it's very likely that you're also going to have a lesion in the fornix. So I think that's a really tricky issue for all of us to deal with. But I was just wondering how your method deals with it. Has to do with effect of lesion size, I think. But
Yeah. I mean, that's what we were attempting to control for when we put lesion size as a covariate in all the analyses. I don't know. Like, I don't think we're getting any negative correlations involving like the fornix. But again,
so I didn't mean it like that. I just
Yeah.
mean like even a positive.
Sure.
Like,
Yeah, right. Yeah, it could be. Like one, in just kind of looking at, in doing the exploration of the data, one thing that I've noticed is that for the, if you make lesion size the target, if you see what tracts are correlated with lesion size, and you covary on aphasia severity, for example, that, I mean, you kind of get what you'd expect there in the large cross-sectional sample, right? Holding aphasia severity constant, people with large lesions tend to have upregulated connectivity all over the right hemisphere, including the core language pathways. People with smaller lesions have upregulated connectivity have higher connectivity on the left. Again, keeping aphasia severity constant, which is kind of what you'd expect. I looked for that in the change analysis. So, where we took the pre-post difference, and that, there was nothing, there was nothing there. Because that was sort of my thinking about, Turkletop's hypothesis, right? That you have if you have a large lesion, you're gonna recover to the right, as opposed to reactivating paralesional stuff on the left. But I actually have a question that maybe we should talk about offline. Is do people find these kinds of negative correlations in sort of standard cortical VLSM studies? Like yeah.
Posterior cerebral artery territory is great because you have to be selected to have a lesion. That's
Yeah.
how you were included.
Yeah.
So, and you think things that cause transient problems, like I suspect some cerebellum and
Yeah.
things like that. I'm sure there's lots, depending on how you select your patients.
Sure. Yeah. Because one difference between this.
is there a possibility of repeating what Chris said, or is that?
Well, I understood him to say that yes, in VLSM studies, depending on how you select your patients, you may in fact find negative, sort of counterintuitive correlations between lesion and behavior, and that in part it can be due to as you said, how you select subjects. Is that?
Yeah, I don't think it's. I would say it's not that these areas are protective of having a problem. It's
right.
To be included, you have to have brain injury, and so areas that weren't critical for the task you're looking at are selecting different vasculature.
Yes, right. So yeah, we're in agreement on that. Although I can't say it nearly as well as he did. But it's not that it's not that having a lesion in the case of VLSM or having lower connectivity in the case of these analyses is protective or better for behavior. It's an artifact of how the sample.
It's the same when we look at surgeries. By the way, when we look at neurosurgeries, and there's areas that removing this has a good outcome from a surgery, and then you could say the lousy kind of stuff also shows that, right? There's always those negative predictors as well, where you selected people based on having surgery.
Yeah.
This is an argument for, this is just a broader kind of discussion, but like including way more patients in our analyses that don't have aphasia, that have lesions in multiple locations. Like, is that, I mean, like if you had a bunch of right hemisphere patients, the patients with lesions outside of the parasitian cortex, is that a solution to these?
Well, we're really trying to come up with how do we help people who aren't coming into our aphasia clinics. And so this is the same population. You want to say what differentiates people with different trajectories, right? Clinically, I don't know, that seems to be what matters.
apologize for our online audience, but because that was inaudible. But on the YouTube version, which is coming up shortly, this will all be audible as well, so you can admire all the wisdom that came out. Is that it for our questions? We don't have questions online. So thank you very much, Will.
Thank you.